Verifying trig identities, example E. So let's see what we have here. It looks like a big mess, but one thing I notice is that on both sides actually, the fractions only have a single term in the denominator. When that happens, sometimes it can be beneficial to distribute that single term into the terms of the top. I could do that here on the left, and I could do the same thing here on the right. On the left, this works out particularly nicely because the first term has a sine x and then 5 cosine x's, right? Cosine to the fifth means cosine x times cosine x, a total of 5 of them. Well, the cosine on the bottom will divide into one of those, meaning I'm left with simply sine x cosine fourth x after I do that division. Let's see, the second term is made up of 5 sines and then a single cosine. Well, I'm dividing by a single cosine, so those two will wipe each other out, leaving me with simply sine fifth x. So just in taking that one step, I don't even have a fraction anymore on the left side. The right doesn't work out quite so nice, but still simplifies things a little bit. First, I would have cosecant squared over cosecant cubed. Well, the 2 on the top will cancel out 2 of the ones on the bottom, leaving me with just a single cosecant x there. The second one, there's nothing really that happens. I can just write it down, 2 over cosecant cubed x. However, I immediately realize, wait a minute, a cosecant x on the bottom is the same thing as a sine x on the top. And so I can just reciprocate this quickly. This becomes sine x. Here, the 2 is already on the top, and then when I reciprocate all of those cosecants I have down on the bottom, I'll end up with sine cubed x on the top. So just doing this makes me feel like I'm getting somewhere. There's no more fractions. Let me go back on the left side, because what I see there is that I have 2 terms, and each term shares a common factor, namely sine x. So I'm going to go ahead and factor that out. That'll leave me with cosine fourth x, and then let's see, I'll have 4 of these left as well because I took one out. And then this is great because as soon as I do this, I realize, wait, I have a difference of squares. I can keep going with the factoring. This is a minus. These are perfect squares. So this will factor in that a plus b, a minus b pattern. What are my a and b? Well, what do you square to get cosine to the fourth x? It would be cosine squared x. Cosine squared times cosine squared would be cosine to the fourth. Same thing with sine. So my a and b are just the squared pieces, which means my factoring will be cosine squared x plus sine x, and then cosine squared x minus sine squared x. Again, if you FOILed all of this out, you would get right back to this previous step. Well, here's where things start to get really nice. Cosine squared x plus sine squared x, there's our Pythagorean identity. That's just a 1, which means it's not really even doing anything. And then as I write down the next step, I'm looking over at the right and I'm noticing that there's only sines. And yet here I have a cosine and a sine. It would be great if I could get rid of that cosine. Well, since it's a cosine squared, I can definitely do that. It's the Pythagorean identity. If I move sine squared x to the other side, this says cosine squared x equals 1 minus sine squared x. That gives me a way to get rid of a cosine squared that I don't want and express it instead in terms of sine x. Cosine squared is 1 minus sine squared. Let's see, and then in that parentheses, I do have a couple of like terms now, those back 2 terms. So I have negative 1 sine squared x minus another 1 sine squared x would make minus 2 sine squared x. And then I figure I must be getting closer. Oh yeah, I think if I just distribute this now, I'll have it. Sine x times 1, sine x, and then here it would be minus 2 sine cubed x. That's it. The 2 sides match. We have verified this identity. Thanks for watching.